Lesson 36, Intro to Logarithms. So, if we were asked to solve the first equation, 2 to the power of x equals 1 over 8, we should know how to do this because we've been practicing that if we can convert numbers to the same base, we can solve for the exponent. The second question on this page, where you have 2 to the power of x equals 10, may be a little more difficult as we don't have a value of a base to a power that's going to equal 10. So let's go through the first one. So if I have 2 to the power of x is equal to 1/8, I can rewrite 1/8 as 2 to the power of -3. From here, because the bases match, 2 is equal to 2, then logically I can claim that the exponent of x must equal -3. So in this case, x equals -3. We could even use set notation to write our solution. If I think about the other side, though, we have 2 to the power of 3 equals 8, and we know that 2 to the power of 4 is equal to 16. I don't know what is in between to get 10. So back in the day, mathematicians were like, well, then let's make this the inverse of this. An exponential form can be written as a log. We have 2 is known as our base. X is known as our power or exponent. And then 10 is going to be known as our argument. When you write a logarithm, you're going to do log with the base of the argument equals the power. So therefore, we can solve for x using logs. Exponential functions are inverses of logs. So if I know exponential form is something like y equals b to the power of x, then I can write its logarithmic equivalent statement as log base b of y equals x. There are some properties that we should know about this. So the base of a log can never be equal to 1, and the base of a log must always be greater than 0. The argument of a log, the y part in this case, is always going to be positive. And that's because if we were to think back to the graphs of both the exponential and the logarithmic, well, let's start exponential first. So exponentials, we have an asymptote in this example as y equals 0 because there's nothing being added. The function's not shifted up or down. And we know that the function's going to look like that. Y equals b to the power of x. If we were to inverse this function, remember that we're swapping the x's and y's, so our asymptote, which was y equals for an exponential function, suddenly becomes x equals 0. So x equals 0 is for my logarithmic, so x is equal to 0 is my asymptote over here. In that case, things about inverses are that they reflect over what we call this reflection of y is equal to x. So a logarithmic graph is going to look like this. And in this case, it's going to be log base b of y equals x. That's going to be my log function. Things, again, we need to know is that domains of logarithms must be positive. You can see that by looking at this graph. The log graph does not cross to the left of x equals 0. So to find a domain of a log, you set the argument greater than 0 and solve. That's a known fact. Okay, let's now convert from exponential form to logarithmic. When we convert, we need to identify the base, the power, the argument, and then we need to use our notes from the last slide to remember that it's going to be log base argument equals power. So for the first one, we would have log base 4 of 64 equals 3. Second one would be log base 25 of 5 is equal to 1/2. Third one, we'd have log base 2 of 1/16 equals -4. For the fifth one, D, we'd have log base x of k equals g. And the last one, we'd have log base b of n equals y. Things that students ask a lot of is, do parentheses matter? The answer to that is yes, especially for the argument. If the argument were to have multiple things like a binomial or a trinomial in there, you want to make sure the whole argument is noted together as a group with parentheses. I use parentheses on that particular example because I have a fraction in my argument and I don't want the 2 to look like it's flowing over into the argument and call that 1/2/16. I want them to be separated by a grouping system. Okay, now that we've converted from exponential to log, let's see what's on the next slide. Well, now we're going to convert from logarithmic back to exponential. So now we have the log form convert back the other way. So I have to remember this is my base of 2. I'm raising it to the exponent of 3, and it's going to equal 8. The next one, I have the base of 1/2 raised to the power of -4 equals 16. Again, grouping matters. If I had just written 1/2 without parentheses to the -4, I'd be indicating that I'd only have 1 to the -4, which would not be equal to 16. B, we're going to have 3 to the power of 4 is equal to 81. And then D, we're going to have a to the power of x is equal to 5. On the next slide, we're talking about two special types of logs. You have a log called the common log, and you have a log called the natural log. The common log is going to be log base 10 of x, which is also written as just log x. Notice that the 10 is missing in this log. That's intentional. That's because we know that if we write log by itself, we're talking in base 10. In a natural log, we write natural logs as ln of x. They just mean that I have log base e of x. Remind yourself what e means for a second. E is a number, and that number is approximately 2.71 ... You find e by doing 1 plus 1 over x to the power of x. If you're more interested in that, please Google e and look into that. In terms of this example that I have off to the right, I'm asking us to simplify or evaluate the natural log of the 4th root of e. A lot of students struggle because they don't see a base on this log, so the first thing I suggest students do is they rewrite it in terms of what they feel comfortable with. If you're comfortable with writing log base e, write log base e for a few times. Then what you want to do is you want to convert this argument. Instead of radical form, we prefer exponential form, so I'm going to call that e to the 1/4 power. Now, again, I'm simplifying, so I'm trying to figure out what this would be. Well, I have to think about the words that I have, right? I have the base, I have the argument, and this whole thing is the argument, to be clear. And I need to find out the power that equals. Well, to do that, I can create it in terms of exponential and maybe figure it out. E to some power is equal to the argument e to the 4th power, the 1/4 power. Well, logically, if they have the same base, just like that example we did with the 2's in the very beginning, then I'm allowed to drop the base and say that the power must equal 1/4. So this guy here must simplify to 1/4. I'd suggest finding homework questions like this, as they definitely show up on future quizzes. Next, you're going to be asked to evaluate or simplify versus solving. When you're solving stuff, you're writing x equals. When you're evaluating stuff, it's just a numerical value. So let's look at the left side. It says log 10,000. Now remind yourself, we just covered what log is without a base. This is known as the common log. So we have log base 10 of 10,000. So I have to think, what power of 10 makes 10,000? Well, if you know your hints about tens, you might know that the amount of zeros is the exponent that 10 is to be that number. So in this case, this equals 4. If you were to plug in your calculator, log 10,000, it's going to give you the answer of 4. So we're good. That's the same answer. If you're solving a question, that means our final answer needs to have an x in it. So in this case, I have to go, okay, well, I know that 10,000 can be written as 10 to the 4th power, and this is 10 to the x. So again, if the bases are the same, I can drop the bases and say that the exponents must logically be the same. So x must equal 4. I also could write this in set notation with squiggly brackets and put a 4 in the center. Okay, let's try some evaluate with logs. So we have log base 5 of 125. To evaluate this, I'm being asked what power with 5 as my base gives you 125. The answer to that's 3. I'm going to write what I said so that people might be able to see what I said. 5 to what power is 125? That's how I got 3. I'm going to write B before I solve it. So B is saying, oh gosh, there's no base. Oh gosh, that's right. We have common log. So common log is 10. So 10 to some power is 1. Well, anything to this power is going to be 1. So we have 0. 10 to the 0 is 1. Last but not least, we have log base 4 of 32 is what? So again, I have to think of this as like 4 to what power is 32? Now the problem is it goes 4, 16, 64, and then it keeps going higher, and I've just skipped 32. So in this case, I might want to create an exponential equation that I know how to solve. Well, they maybe convert to lower bases, so I have something like 2 to the squared, which that's 4, and then x is the power I'm looking for, equals, and then 2 to the power of 5 is 32. Okay, so this is looking good. I'm looking like I'm getting the same base stuff. My bases are the same, so I'm allowed to say exponents are equal, so 2x equals 5. X must be 5 halves. Now go back to the question. Does the question have an x in it? If you answer that with no, then you need to remind yourself that this answer is just 5 halves. There is no x written in this answer. Why? Because this said evaluate. It also could have said simplify. Either or give you just values, no x equals. Lastly, we get to the last slide of this lesson, and it's solve. If you're being asked to solve logs, you want to rewrite them in exponential form and then solve for what's being asked. So for A, it says that you have log base x of 81 equals 4. If you rewrite that in exponential, you'll say x to the power of 4 is 81. Now you might not know that off the top of your head, so I might think of it like this. X squared squared is 81. Because I do know what 81 is if I square it. So I know that x squared must be 9. Therefore, x is 3. Now, if you think about this, sometimes people might be like, well, it could be plus or minus 3 because I'm saying it's x squared equals 9. But if I go back to what the rules are for logs, I know that x can only be positive numbers. Therefore, x is 3. If I look at B's example, oh, this one looks fun. Log base 3 of a log base 2 of x equals 1. So what I'm going to do is do this let statement. Let u equal log base 2 of x. So I'm going to rewrite what I'm looking at. I have log base 3 of u equals 1. I'm going to convert that to exponential form. 3 to the first power equals u. So that means that I can claim 3 is equal to u. Okay, but u is equal to log base 2, because I already wrote that. U is equal to log base 2 of x. So I can now say log base 2 of x equals 3. And then I can do, again, exponential form off to the side if I need to. And I can say, well, then that means that 2 to the power of 3 equals x. So therefore, your answer is 8. Last but not least, you have the natural log of x equals 4. Again, if you're someone that struggles with the natural log because you don't see the base, rewrite it. Log base e of x equals 4. Convert it to exponential. E to the power of 4 equals x. I'm not requiring you to know what e to the power of 4 is. Simply write e to the power of 4 and you're done. Have a great day. That's the lesson.